Okay, so second last week, can't believe semester's about to end. It felt as if it just started a few weeks ago, but that's modern universities for you. 12 weeks of lecturing against, I guess, 25 years ago, about at least 26 lectures in a semester. So, we're going to talk about an algorithm, but then the motivation of this topic is not just to present a new real-world algorithm, which has always been a focus, mainly when I designed this unit, one algorithm / data structure, real-world per week, but then also take the opportunity to introduce something fairly profound in computer science, at least as an introductory topic. So we're going to talk about a specific problem, matching of a specific kind on bipartite graphs. And much of this lecture will be reminiscent, at least in the way the algorithm proceeds. Not the details, but at least in broad strokes, it will be reminiscent to the kind of algorithm that you use to solve min-cut / max flow in 2004. We have covered min-cut max flow in 2004, that's correct. And also this sort of continues the discussion we started, at least the introductory things that we started about simplex algorithm, linear programming formulations, solving a linear program in a standard form. And this sort of this kind of algorithms that we're going to learn today are the problems are called primal-dual problems, and these problems can be solved using simplex. Usually the network flow problem, let's take for example, is a classic primal dual problem. The min-cut is one form of the problem, the dual is max flow. Solving for max flow automatically solves for the min-cut. So remember the algorithm that we used, the Ford-Fulkerson's algorithm, where there was this notion of a flow network whose capacities are given, and you want to find a flow assignment conserving certain simple rules of flow conservation. And in the whole algorithm, you had this alternate view of the flow in terms of what's called a residual graph. If you recall, if you've forgotten, that's fine, but there'll be another object on which you're augmenting. So you have this real problem, and then you have the whole dispensation of how the algorithm needs to augment the objective function on the residual graph. So you try to find any augmenting path from source to sink. That gives you a bottleneck. That bottleneck allows you to update your flow assignments, and it goes in a cycle to a point where you can no longer find an augmenting path on the residual graph, which means that you can no longer augment the score, and somehow magically min-cut equals max flow proved to you that when you don't have an augmenting path on the graph residual, you have not just found the minimum capacity cut. That's what min-cut means, that you cannot reach the source, so sink from the source. So that means that you're going and you get stuck somewhere, and there's a cut on the vertex set which doesn't allow you to bridge that gap onto the other side. And then it turns out that that cut gives you the notion of what a min capacity cut is. And because you can't augment it, that becomes a max flow. Okay, that's the problem that we dealt with. Now, I have some introductory slides about network flows, but and usually what I do is I start by jogging your memory about Ford-Fulkerson and then maybe a version of a problem which I just want to check this with the students here. Did anybody do maximum cardinality bipartite graph matching in the TUTE at least as a special case of Ford-Fulkerson? So if you're given a bipartite graph, you want to find a matching where the number of edges in the matching is maximized. Nothing about the weights, it's an unweighted graph, unweighted bipartite graph, not reminiscent. So what we can do is, what I usually do is introduce the maximum cardinality version of bipartite graph and then talk about this special problem which is called minimum cost, that's much like min cut, there's a min cost bipartite graph matching. So if you have a bipartite graph which weights on it and costs on it, you want to do a matching that minimizes the cost. So I think what I'll do is, I'll do something slightly different to what I usually do on this topic. Much of the initial part is non-examinable, it's only to jog your memory. But rather than jog your memory, I'll get into the problem and then maybe jog your memory at the end. Okay? If I don't do it, if I don't end up doing it now, I can pick it up at the start of the next lecture anyway. So don't worry about it. So most of this slide, I just wanted to give a heads up that we'll come to this in a bit, but much of the red highlighted slides are non-examinable, so don't worry about them. They're basically talking about Ford-Fulkerson analysis and so on. So let's actually start with a very simple definitions. So we're going to do, the examinable bit is optimal matching on weighted bipartite graphs. I'll jog your memory about, or at least I'll do a revision about Ford-Fulkerson in broad strokes and tell you how to solve a lesser variant of this problem, maximum cardinality. One is trying to optimize weights, one is trying to optimize the number of edges in the matching. That's the only difference. One's in the unweighted graph, this is non-examinable, the weighted bipartite graph is examinable. Okay, don't worry about the mathematical definitions, it's meant to serve as your lecture notes when you sit down quietly and absorb it, but just follow me in my descriptions. So what's a bipartite graph? As the name suggests, bi, two, partite, partition graph, a graph whose vertices can be divided into two sets. But in a way you could divide the vertex set into two any number of ways. What's so special about bipartite graph? If you actually look at the example there, there's a vertex set X and a vertex set Y. So when the total number of vertices in a bipartite graph is all the vertices in X and all the vertices in Y. But if you look at the edges have a special property. You never have edges between vertices in the same set, but you have edges that go from one set to another. Does that make sense? So that's bipartite graphs are ubiquitous. They kind of arise in many modeling, real-world modeling tasks, and you usually have algorithms that deal with graphs of this kind. Any questions about what bipartite graph means? Okay, that's what this is saying. What does a matching in bipartite graph mean? So, well, if you took some subset of vertices in set X and some subset, an equal number of vertices as that subset in set Y. So let's say if you've selected 3 vertices in that set X, the green set, you would have to select 3 vertices in set Y, and you have to have a matching that ensures that every vertex in that subset that you've selected has exactly one edge as its endpoint. So edge will have 2 endpoints, 2 vertices as the endpoints. So you would not have a vertex matched to anything else. It's a one-to-one mapping between the subset of vertices in X and a subset of vertices in Y. So in principle, there are many ways in which you could select these matches. the matches, depending on the graph that original graph that you have. Let's assume that all the bipartite graphs are complete. Complete meaning that if there are n vertices in the first set and m vertices in another, there's an m times n possible ways in which you can connect. Right? Each n connects to anything else, but sometimes in some problems you don't have all of those n times m. You only have a small fraction of what of the possibilities. Think of those missing to be edges that are infeasible, or if they are weighted, they have weights which are infinite. But the matching here has got nothing to do with the weights of the graph. It's just saying how do you pair up vertices in one set with another. So the subset of vertices out here. So here it turns out that the subset is x1, x4, and x3. So that's x1, x3, x4, and then y1, y2, y3. That defines a matching between x1 is matched to y3, x3 is matched to y2, x4 is matched to y1. And this is one of the many possible ways in which you could do the matching, right? There's nothing special about this definition. I haven't selected this matching trying to optimize anything. It's just a matching. Okay, it's just a pairing up of vertices. Now, what's the cardinality of this match is basically how many edges you have in your matching. So what's the cardinality here in this example? So it turns out that the cardinality is there are 3 red edges. So the cardinality of the matching, which I'm using with these vertical lines, m is the matching, the size of the matching is 3. That's how you read that. Okay. Is everything clear up so far? I just want to emphasize that the moment you say the cardinality of a match is some number, 3 here, the vertices would be 2 times the matching, because there is every vertex is an endpoint of exactly 1 edge in a matching. So if there are 3 matches, then there has to be one distinct edge on one distinct vertex on one side and another distinct vertex on the other side. So 2 per edge. So 3 times 2 is 6. So there's 6 possible. There are 6 vertices, 3 in the first set, 3 in the second set, and the cardinality is 3. And there are many ways in which you could match these. So obviously, I could have matched it this way. I could have matched it this way. I could have matched this way. Cardinality of this is 3, cardinality of this is 3, cardinality of this is 3. I could have even had a cardinality 2 matching by dropping one of the yellow vertices and dropping one of the green vertices, and there could be many possibilities. I could have a cardinality of 1. I could have a cardinality of 0. Nothing matches with anything. So what does the maximum cardinality mean? It means that I have to pick a matching where the number of edges is maximized. The number. Nothing about the weights of the edges. It's unweighted. It's maximized. And that's not at all unique. In fact, it turns out that the maximum cardinality is 3 for this problem. Obviously, it can't be more than 3 because y has only 3 vertices. You cannot have a cardinality of 4 for this problem, right? And there are many ways in which the maximum cardinality can manifest. Often when people talk about maximum cardinality matching, they talk about any one of them. Not all of them, any one of them. Okay? Can you find me a way of matching vertices in one set to another set given a problem? Okay? When I was teaching 2004, I would have an exercise about student wanting to do IDL, IDL being one set, students being the other set, or trying to as IDL coordinator doing a matching between students, and there's some variation of them in terms of preferences and so on. So these are real world problems, so you could model. Most of the graph problems are idealizations of something that is real world. You model them to a graph problem, and then you attack it using the algorithm graphs. That's how it works in general. Okay, what is a perfect matching? Now, perfect matching has a specific meaning, right? So if you look at a bipartite graph, vertices in the between the two vertex sets. The green, there are 5 vertices. The yellows, there are 5 vertices. Yeah. Set green, set yellow. So perfect matching is a matching that covers every vertex of this graph. The graph contains a set of green vertices and yellow vertices. So bipartite graph, because there are no edges between vertices in green, no edges between vertices in yellow. And a perfect means that you are ensuring that every single vertex in one set has a counterpart in the other set. It's perfect. It's perfectly matched. Nothing is unpaired. And that usually happens when you have that usually happens. When I say that usually happens, it only makes sense when you have exact number of vertices in one set matched with exact number of vertices in the other. Okay? Because all of them have to match. If it's perfect, then if there's unequal number, then there's a problem, isn't it? You can't, if there are only 5 and 3 in the previous case, you can only match up to the maximum cardinality is no more than 3. So there'll be 2 of them in the green that will still be unmatched in the previous case. But here, if you have an instance where you have equal number of vertices, you end up with Any questions so far? It's starting slow. I'll skip over all the non-examinable slides and jump into the problem straight away and then come back to it at the very end, okay? So don't worry about all this. It was meant to give you a motivation. Okay. So we will now talk about a specific problem, min-cost bipartite graph matching problem. A min-cost implies that there is some cost function on this bipartite graph, okay? Now, this problem is also called linear assignment problem in the literature. There is a quadratic version of the assignment problem, which is an advanced topic. Maybe in grad school you would hopefully come across. These days, grad schools don't come across it much in terms of reading, but this is basically a linear assignment problem, and we'll see why why we qualify it as linear in a bit. And there are many instances where you would want to deal with a cost function over a bipartite graph that you want to minimize. Okay, let's take this problem statement. So let's jump into the problem. Now, think about this artificial problem where there are n agents and n tasks. Automatically, the problem is stating that there are equal number of agents and equal number of tasks associated. Yes? So maybe my battery is not working. Okay, the battery is dead, so I have to stick to the mic. Maybe I'll have to stick to the lectern. Is that good enough? So I'll just move away from the mic. Am I still audible? Okay, thank you. So it looks like for those who are on the live stream, I had a lapel mic on me, except that it has no battery. I think the battery got drained, so I wasn't aware that it was running low on the battery, so switched over to a different audio mic. So we're talking about the problem statement. The problem statement is that there are n number of agents and n number of tasks. Automatically, we know that the number of vertices modeling the agents is n, number of vertices modeling the tasks is n, the same number. And you have if you match an agent to a task, if you assign an agent to a task, there is a certain cost, maybe the amount of money that you would have to pay for the agent to complete the task, so to speak. So there's a cost associated with pairing up an agent with a task, and then you want to find an assignment where one agent is paired with one task is paired with one agent in the reverse way. So, and then you want to do that so that the total cost of the matching, the assignment, not your assignment 1, 2, 3, but the assignment matching of the bipartite vertex in a bipartite graphs, that matching is minimized to total cost. So if you look at this cost matrix, assigning task 1 to agent 1 is 198, let's assume, dollars. Task of assigning agent 1 to task 2 is 172. Similarly, task 3 would be 300, and so on. Okay, so there is a problem clear about how to actually see this as a bipartite graph, and so that's the cost matrix. I can see this as a bipartite graph with one side, one partition being the agents, one partition being the tasks, and then there are edges associated with it. Now, I already told you that sometimes you might, if the graph is given, rather than the matrix, if the graph is given with only few edges of the n squared possibilities, because n is the number of edges here and n is the number of edges on the second set, so total number of edges would be n squared, n times n, n plus, so there will be n times n plus n plus n times, so that would be n squared. So, and when you're doing, when you have only a partial number of edges, you can think of an edge with infinite weight. Okay, if there's some edges missing, you can say that it's an infinite weight, which means that you're still minimizing under the objective, but if you select infinite, it becomes infinite cost, right? If you select any edge where an infinite edges is selected as a matching, it's infinite cost, so it will stop it from, if you have a viable perfect matching, it will stop you from selecting that an edge with an infinite cost. But in this case, all costs are finite, it turns out, but in principle, you could have had a bipartite graph that's not completely defined. You could only have it incompletely defined with edges, with weights. So if you had this problem, it turns out that the min cost perfect matching for this problem is that assignment. Agent 1 assigned to task 2, agent 2 assigned to task 3, and agent 3 assigned to task 1. Okay? Can you see that? Now, it's important to note that while it appears as if I've selected the minimum in the first row for agent 1 and a minimum in in that last row for agent 3, surely I didn't select the minimum in row 2, isn't it? So you can't greedily choose the minimum and then think that it would be a matching, a viable matching, because the matching means that it needs to be distinct, right? So you cannot choose, once you have chosen task 2 for agent 1, you possibly couldn't have chosen the same task for agent 2. That would have been an invalid matching, isn't it? Because you have two agents mapping to the same task, but you need to have distinct, okay? Now, how do I rationalize this problem? I'll just put my mic down and hopefully I can still be audible. Let's see. Because I need my hands free for the moment. All right, so you can think of this to be what's called the original cost matrix. I'm using the word original because obviously something's going to happen to it eventually when we're writing the algorithm. And you can think of an assignment, let's call this C, this cost matrix C, and you have an assignment which I'll call capital X, and I'll tell you what these mean in a bit. Now when I say Cij, I mean that the cost in ith row and jth column. Obviously, when you have two indices, so if I say C2, 3, I mean that, isn't it? Second row, third column. Now, associated with this cost matrix would be an assignment matrix. Assignment tells you which agent has been paired with which task. So X is the agent, so agent 1, 2, 3, task 1, 2, 3. I know that whenever I see a 1 in that matrix, I know that agent 1 has been assigned to task 2, agent 2 has been assigned to task 3, agent 3 has been assigned to task 1. So what happens to the rest? Well, the rest would be 0, 0, 0, 0, 0, 0. Okay? An assignment is of that kind. So two matrices, at least in your head, you can think of a cost matrix and an assignment matrix that overlays on top of it. Okay? So when I have to think about an assignment, what are the constraints of this assignment? Can I have, if you look at first row of the assignment matrix X, so when I say Xij, I mean some value in the assignment matrix which can only be a 0 or a 1, right? It's a Boolean matrix, it's a binary matrix. So if I look at a value of Xij in the first row, how many ones should I be able to see in the first row? It has to be 1, isn't it? Every agent has to be assigned to one task. That's a constraint for matching. So if you sum up all the elements in the first row, you should get 1 because there's only one instance of 1 and everything else is a 0. The same holds for the second row or the third row or the fourth row, go all the way to the nth row, isn't it? There's nothing special about the first row, right? So all the summation of these values, this has to be the sum should be 1. Sum is 1. 1. Now, what about the columns? If I add all these values in a column, in any column, should it add to 1? And the reason is that each task from the other point of view has to be assigned to a unique agent, right? So summation of the rows and columns has to be added up to 1. Am I good so far? Okay, I have to remember myself that this is there, but it's a tragedy for those who think that not coming to the lectures is okay, but technology can fail, so I can try my best. Thanks. Keep reminding me if I'm moving away. Piyumi, thank you very much. All right, so we talked about what X and X and C are. So let's formalize this problem. Now, by the way, I just wanted to say that if I want to find a min cost, how do I find a cost subject to this assignment? If I multiply each value in the matrix X with the corresponding value in the matrix C, would I get the total cost of the assignment? Why is that true? If 198 times 0, that will become 0, plus 172 times 1, that will become 172, plus 300 times 0, that will become 0, okay? And if I keep adding those corresponding terms, 185 times 0, plus 200 times 0, plus 225 times 1, plus 158 times 1, plus 175 times 0, plus 200 times 0. If I did that, all the zeros will cause everything else to disappear except those highlighted ones. So that would be a linear sum of wherever you saw 1 in your X, those costs get added up. And that's what you're trying to minimize. Whatever assignment that you come up with, whatever matching you come up with, the sum is minimized. Is that clear? Okay, so if that's clear, we want to minimize double summation over rows and columns. That's go through all possible rows and columns. Cost times X is what you're doing. The assignment times the cost. Is that clear, everyone? So that's what we have done. Out here, just that Xij is the values in X, Cij are the values in C, and you're trying to minimize that. That's the objective function. What are the constraints? My Xij can only be 0 and 1. They can't be 0.5, they can't be 0.7. They either assign or not assign. And then if I take, let's say that I was the row variable, so summation over all possible, let's fix a j. When you fix a j, you're fixing a column. Summation over the column is 1, summation over a row is 1 is the second constraint. Summation, so you're saying that between those two, the columns should add up to 1 and the rows should add up to 1. Here, it's saying that fix a j, and for a fixed j, sum over all possible i's for that fixed j is 1. Similarly, for a fixed I, summation over all possible xij over from j equals 1 to n equals 1. So when you fix j, you're fixing a column. When you fix I, you're fixing a row. Does that make sense? So all I've done is define a problem. Now let's see if these observations would make sense. What's observation 1? Adding a constant value to any row of the cost matrix C does not change the optimal assignment, does not change X. It might change the cost you end up getting, but it doesn't change the answer you would want to make. Does that make sense at all? Because if you add a constant across a row, everything has been monotonic, has been proportionately increased. The decision of which one is minimum would not change. If you added different terms, you would have a problem. But if every single element in a row is added by the same amount, a row of that cost matrix has been added up. It doesn't change. That's the reason the decision doesn't change. You still have to choose one of them, and all of just been added by a constant, so your decision is not going to change. Similarly, if you did the same thing for a column, it doesn't change. So remember this when we are going through the algorithm later on. Okay? Before we go to the algorithm, there is some amount of history that we will go through. So the method of solving it is called the Hungarian algorithm. It's called Hungarian algorithm because of an insight that Kuhn is the person who first came up with this idea. Kuhn and Munkres were the first two people around 1960s who came up around 1950s, it turns out. So I think Munkres was in late 50s. Yes, that's correct. So Kuhn and Munkres, they came up with a method of solving the min-cost problem. And it's called Hungarian because they used a certain insight, and we'll see what they incited later on, by Koenig and Eguvari. If I'm mispronouncing the accented kind of phonetics, then I'm sorry about that. So Koenig and Eguvari are the two Hungarians whose insight Kuhn had used, and Kuhn and Munkres really. They both independently came up with a solution towards this problem. And then the original formulation runs n to the fourth. It's polynomial time. You can solve if you had n vertices, n being the number of vertices in each set. That be the total, the graph will have 2n vertices, one n on one side and the n on other side. So you would run it on n to the 4th algorithm polynomial, and Edmond Karp, in fact, that this algorithm, if you've done network flows, there's a variation of Ford Fulkerson called Edmund Dinich, Edmund Karp. The same set of people were working on related problems, network flows, and on one side, and weighted bipartite graph matching on the other side. They showed a provably optimal algorithm. So this is, you can't do better than n cubed for this algorithm. So they came up with that. This is mainly a history. We will probably go through the version that naturally leads to n to the 4th in the worst case, but in practice would be n cubed for you. I'll tell you as a feedback, I mean non-examinable observation of how Edmund Karp came up with the n cubed approach. It should be easy to implement it if you understood the original method. Yeah. So, okay, this looks more serious than it really is, but I think we need to understand this formulation a bit from the math point of view. So remember this function, objective function we wanted to minimize. So z equals double summation of cost times the assignment. That's what we had. Okay. So what this Hungarian method does is, this is your cost matrix. Associated with the rows in, so rows in your cost matrix and the columns in your cost matrix, what it does is it tries to maintain a row variable u1, u2, u3, un, v1, v2, vn. So there are row variables called u's and column variables called v's. Now, when you first come to the algorithm, why is all this? Now, I want you to reflect back on what we discussed in linear programming. So we introduced the slack variables s, t, and u for a linear program, isn't it? Okay, they're sort of those variables that are trying to keep track of some slack, because all these programs are related to the linear programming formulation. So think of, if you don't yet know what these variables are, because I've not introduced it to you, think of them to be some slack variables, and we'll see what that slack means when we do the algorithm. Okay, so what did I say? This is our objective, and before we did anything to it, think of this variables u's for the rows and variables v's for the columns that exist associated with the cost matrix. Now, what I can then do with this objective function is, if you look at that term here, that term, oh sorry, I should have, where is the eraser? That term. So x is that one. So Cij, I'll just, Cij has been changed to that form. So what did I do? Well, this clearly holds. This is nothing but Cij, because I can cancel this out, and it will be Cij, isn't it? Cij, I've just rewrote Cij in terms of whatever I subtracted ui, whatever j, I subtracted vj, and also added them back so the equivalence holds. So ui and vj are the row variables and column variables associated with the cell ij. Okay? Is everyone clear about that equivalence? So all I'm saying here is that that term is same as that term in the parentheses. Now, if you agree to that statement, and I don't think there's anything major there beyond the fact that what is this u's and v's, we'll figure them out later on, beyond knowing that there are row variables and column variables, which you can intuit as slack variables associated with rows and columns. Going from here to here is fairly trivial, right? So think of the terms being divided into 3 parts, part 1, part 2, part 3. And if I distribute the summation and xij, so that summation is for all of those terms. So if I distribute them, I can distribute them over those 3 terms. So I get that term, and that term. So 1, 2, and 3. Can you see that I've just distributed the summation into the set of 3 terms? I've not done anything major. Now, is everyone on the same page so far? Okay, so we are here. Coming to here, this term is same as this term. There's nothing major there. Now, but something special is happening here. So look at that term there, it's double summation, so for all possible. So double summation, see them as going through every cell in the matrix. So you're going through, double summation is the 2 for loops that you would write to go into every cell in the matrix, right? That's what double summation means. So for every cell in that matrix, you're doing xij. Xij is a value that is 0 and 1, 0 or 1, right? So times ui. Ui is a row variable. It's a variable that you introduce to the row. Now look at the inner summation. Inner summation is over j equals 1 to n. Okay. So for a given I, outer summation for a given I, the inner one explores all possible j's, isn't it? What happens to ui? Ui doesn't change with j because it's a row variable. It's always a constant for the inner loop. So I can take that constant out. So essentially, I got this constant out of the inner loop, basically, if you see it as a loop rather than a summation. So if you just take it out, I end up getting that form, the form that I see here. Similarly, out here, the only difference is Vj is constant for, if I swap the order of the summation, I will not change. So you can go through the loop in a row major order or a column major order. So go through a matrix, you can go row-wise or a column-wise, so that's equivalent to swapping the summation sign, isn't it? I could have written this as j equals 1 and I equals that way. I could have swapped the order. It would not change the meaning, the semantic of that term. And if I did that, then Vj is constant in the inner loop, the swapped inner loop. So now I have that expression. So all I have done is a series of transformation after introducing the row variables and column variables. Is everyone clear about how I got this far? From here, it should be fairly straightforward. What is this? Summation of xi's in a row. J equals 1 to n, because j's are the column variable. That is over a column, over a row, the column is changing. So that is nothing but 1. That's what we said. And similarly, that's nothing but 1. Okay? We said that in the previous slide, didn't we? I'll show you. Didn't we say that's 1? Okay, so that's what we are applying the rule there. So those 2 things are 1, which means that I can transform this to this. So where that term is same as that term has now become that term, and that term has become that. Is everyone clear so far? I mean, these are algebra. It's got nothing to do with insights as much as some transformations have done, some special transformation. But getting to this form will give you $1 million insights about how the algorithm works, right? So now, I will focus on the term, the partial term in the first part, so that the whole part, that's the first part. It's double summation of xij, that's the assignment, times cij, the cost, minus the row variable, minus the column variable. For any ij, everything has cij minus ui minus vj in this formulation, isn't it? Now, I will call this term C prime ij. What is C prime ij? Cij minus row, ij gives you the row comma column. So Cij minus row variable minus column variable, ui minus vj. Okay, that's what I'm going to call C prime ij. Now, I will use the word reduced cost to mean that. I'll tell you what the word reduced means in a bit. There's the original cost Cij, but if I subtract it with a corresponding row variable and a column variable, then it becomes reduced, C prime ij. Now, so I'm giving you the motivation before we do the algorithm, right? So we were here, let's go to the next slide, which is exactly what we saw in the last line. That's what we changed that function to. Now, forget about the text here, just focus on what I am saying. Will you agree that xij is either going to be 0 or 1? Correct? So assignment can either be in the matrix is 0 or 1, correct? Now, if xij is 0, if it is 0, what happens to the first term? Obviously 0, isn't it? If you multiply double summation of 0 times anything, it's going to be 0. For all possible zeros you see in the assignment matrix, that term doesn't exist. It goes away. But there is this problem that there are some, at least one in a row slash column, no, exactly one in the row slash column that you'd want to achieve, where xij is 1. And this, if it's 1, whatever I'm reducing the cost to will contribute, so that objective function is identical to what we started with. So that your choices of ui and vj, and currently ui and vj are variables. We don't know how we've selected them, what they even mean. But then if I do a cij minus ui minus vj, it will come up with some value. Whatever the values of ui and vj are, it will come up with some value which is different, reduced from, or different from cij, the original cost value, right? So now, what the Hungarian algorithm does something clever. It says that, now, how do I change this problem of minimizing the original objective to a different form, okay? So that whenever I'm making an assignment, whenever xij equals 1, those ui and vj's are so selected that reduced cost becomes 0. So how do I select ui and vj? So think about linear programming for the moment. So we had these corner points where something became zeros, right? In the linear programming, when you're exploring the corner points in the standard form, so fixing some values to 0 to evaluate some values on for the decision variables. So the question is that what values of u and v's can I fix to the matrix, the entire matrix, such that whenever I do an assignment, cij minus the row variable minus the column variable, wherever there is an assignment of xij equals 1, that value c prime ij becomes 0. If that was true, if that can be achieved, let's see what that means in a bit, but if that can be achieved, then do you agree that if xij equals 1, that becomes 0, and if xij equals 0, then in both cases, 0 or 1, so let's assume xij is 0 or 1, this whole term becomes 0. Because if xij equals 0, the term becomes 0 anyway. If xij equals 1, I'm making sure that cij minus ui minus vj is 0. Because the choice of selecting ui's and vj's are entirely on me. Okay? So, and then the focus is only going to be on the term if I'm ensuring that by selecting ui's and vj's in some special way, I can ensure this term disappears away, then my objective would be involving only ui's and vj's. Now clearly, if ui and vj is 0, okay, think about what happens. If ui and vj is 0, you would basically end up getting exactly the same objective function as you started with, right? Everything becomes, so if ui and vj's are zeros, that means that you have the original objective function, and if I keep increasing ui's and vj's, and by the way, these are ui and vj's not independently chosen because ui is a row variable. Assignment is done only on one value in the row. Okay? So whatever ui and vj's, they affect all values in the row and all values in that column. They are not independent decisions. So somehow there is this tendency of, as I increase this value, I can force cij minus ui minus vj. So let's think about cij to be some positive value, just to think about it. I can choose ui's and vj's such that as I'm increasing ui's and vj's, that value tends to 0. Ci minus ui minus vj, cij, so this term, cij minus ui minus vj tends to 0 as I'm increasing ui's and vj's, okay? So if the key point is that whenever the assignment is done, I need to achieve this strict equality. What does it mean? Instead of writing it as ui minus vj, that's v. So that's what this term is, c prime ij. And if I'm setting it to 0, I'm essentially saying cij equals ui plus vj, isn't it? If that's what this statement means. And then there is this constraint that's saying that because I can start off ui and vj's with zeros, I'm increasing it, but I want to make sure that the sum of ui and vj's for any value of the cost in the cell, the sum of them is always less than or equal to the cost. So cost is greater than or equal to the sum. That's the constraint that I'm making. And then it says that, and we'll see why this is true, that while I'm making these selections, I'm only going to do an assignment of xij equals 1 when cij minus ui minus vj is 0. The zeros, the reduced cost will have to be zeros in wherever I'm assigning. And if I end up choosing n such assignments, if I end up choosing n such zeros in the rows, in the reduced cost matrix, C prime ij matrix, then I not only terminate, I terminate correctly. That automatically becomes my min cost assignment. And this is where it becomes very reminiscent to min cost max flow problem, min-cut max flow problem. The min-cut max flow problem, what did we do? We terminated. You knew that when you terminated, you have reached simultaneously the min-cut and the max flow. You didn't do anything beyond just augment, 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 augment without any care for the objective function, just because the way you have done it guarantees a special relationship between max flow and min-cut. Now, maybe it's a very good point to actually discuss briefly what the min-cut max flow does in terms of the idea of how that relationship holds. So if I'm on the board right now, so we're talking about min-cut max flow, which is from 2004. So think about a certain scale, a certain range of values that min-cut and max flow takes. So what was the major observation? If you remember the theorem, it says that any flow, okay, let's call this flow and cut for the moment. For any flow is a lower bound on any cut. So one of the first things that you would have proved in doing min-cut max flow is to prove that there was a relationship, that any flow that you can evaluate on the flow network will have to be less than or equal to any cut that you will have to define on that flow network. And this is if you go back and listen to the proof that somebody should have offered you in 2004, that would have been hell. Now, is a min-cut any cut? It's one of the cuts, isn't it? It's a special kind of cut, rather. It's any cut in the sense that it is a cut, isn't it? So when I said any flow, any cut, it also means that any flow has to be a low bound on min-cut. Okay? So this statement is true that any flow would be less than or equal to a min-cut. And in fact, by that same thing is a max flow flow. So max flow has to have that relationship, should be a low bound to a min cut. Now, when you end up, so think about the current state of the flow assignment, you get to a point where you can show that you got a cut that is whose flow value is equal to the cut value. That means that by the definition of a flow being a low bound on a cut, you have simultaneously maximized the flow and minimized the cut. Because if you exceeded the cut, the low bound flouts, right? The strict equality makes sure that the min flow equals so min cut equals max flow. Isn't that how you went about proving it? I mean, and there were more to the proof, but I'm just giving you the gist of what you did. Now, it turns out that what we're going to do here is something similar. So the moment, now we come to the current problem where you have min cost and this some maximization that we will do, so that while we maximize something, it is, if I get to an assignment, a perfect matching is a matching where all vertices are matched. When I get the cardinality of my match while I'm doing it equals n, the moment I get that to that point, I can no longer reduce my cost matrix, which means that I can stop. And wherever I stopped, I can show that by the definition of a bound, of a lower bound, we'll see on the next slide, you will never get a matching that has a lower cost than the one you stopped at. Exactly like the argument where when you stop the Ford Fulkerson trying to maximize the flow, at one point you stop, you can no longer augment the path because you can't reach the sink, and you stop. Wherever you stop gives you max flow solution. And how do you get the min cut from that? If you just found all reachable vertices from the source, the set of reachable vertices is the min cut. Cut is nothing but a partition in the graph. So that is how this is. They are under the same class of problems where, like the linear programming, you start with a value of 0, you keep augmenting, you're always incrementing, flow always improves, it never goes back. In your flow, Ford Fulkerson, in simplex, you never get an objective function that is less at any instance. And at some point, you keep increasing and you stop, isn't it? And you stop because you cannot, and the moment you stop, you know that you have reached the optimality. In simplex, that's also the case, isn't it? There's a point where you cannot increase the objective function, you stop. And you know automatically that you've reached the optimality because of the way you've processed the algorithm. Same thing with max flow, Ford Fulkerson, same thing with what we're going to do. So the original formulation is to minimize this objective function subject to those constraints. I've shown you how, using this special UI and VJ, row variable and column variables, I can change it to maximize this objective function subject to the constraints that for every I comma j, for every cell, its row variable plus column variable is less than or equal to cost of ij, or other way, previously I wrote it the other way, cost of ij is greater than or equal to ui plus vj is what I've written. Now, why does this hold? Why does this special formulation, why is it legit? Before we jump into the algorithm, this is the last slide about the theory before we talk about the algorithm. But it's a very important slide to digest that we really understood. So what's our goal? Our goal is to find a perfect matching. A matching where a vertex, every vertex in the bipartite graph is matched, has a counterpart, subject to the fact that you're minimizing the cost function. The cost function is associated with every edge. The total sum of the costs is minimized. Now think about any feasible matching. What is a feasible matching? Any matching that has whose cardinality, the size of the matching is n. Any of them. I'll call them m prime. Take any matching, it will have a cost, right? Because any matching will have a cost. They will have edges. Each edges will have a number, and you just add up the number. It's a cost of that matching. So if you took the cost of that matching, I sum over all the ones, the assignments I've done for that matching, all the ones, xij equals 1s in that matching. If I add them up, now, because I'm ensuring, what is the previous constraints? Ui plus vj is less than or equal to cij. Another way of saying it is cij is greater than or equal to ui plus vj. Because of that relationship, I can show that this term here, let me scribble on the board, scribble on the slide. This term here, you understand that term, right? So it's basically every possible cost of every possible assigned pair of vertices, every possible edge that's in the matching really, is greater than or equal to that. Why? Because every cij is greater than equal to ui plus vj. Because of that relationship, this holds, isn't it? Okay? Now, if that's were true, do you agree that a perfect matching, a feasible perfect matching. This is not a min cost matching, it's a feasible, any perfect matching which has a cardinality of n. If it has a cardinality of n, in every row, there will be at least one cell that is assigned. And every column, there's at least one cell that's assigned. So there would be one, the summation over each row will be one, summation over every column would be one of xij's, right? So that's what a matching is. If, let's actually look at an example to get that intuition clearly. Okay, let's go to this example. Okay, let's look at that assignment there. So what are the ij's that matched in this thing? The ij's are 1 is matched with 2, then 2 is matched with 3, and then 3 is matched with 1, isn't it? That's what the matching is. It happens to be a min cost. It doesn't matter if it's min cost or not. It's any matching will be of that kind. You can come up with any matching. If you want a different matching, let's take a, maybe for the heck of it, let's say that you've matched this way. Okay, so those three things. So 1 is matched with 3, 2 is matched with 2, and 3 is matched with 1. So that's a feasible matching whose cardinality is 3, n equals 3. Okay, the 3 edges in that matching, correct? So if that's there, do you see that if you look at the row variables, you'll find all numbers from 1 to n, 1, 2, 3, obviously, because if it has n, the cardinality of the matching is n, then you will have all the row variables represented there, 1, 2, 3, 4 in that order that you've enumerated. Similarly, if you look at all the j's, there, in some permutation, you will have to see all possible values of 1 to n. That's what a matching is. Something is matched to some row element is matched to some column element. The sum total over the row is 1, sum total of the column is 1. So in some order, if you look at the i's and j's in a matching, you will, in the rows, you will see all values from 1 to n. In the columns, you would see all values from 1 to n whenever you see a feasible matching, any feasible matching. Now, if that insight is clear, if you look at this sum here, for all possible I, j's in a matching, I am adding the row variable and a column variable. So if I'm able to see every row once and every column once, I can split this term into that term, because I've just said, okay, sum up over all the row variables, sum up over all the column variables. That it's possible because your any feasible matching will have all rows in it, all columns in it. And you're just adding up once each of them in some order. That's what a summation means, isn't it? So if I had, maybe it's easier if I have a concrete example. We said 1, 3, 2, 2, 3, 1 in that previous example, right? So if I have to sum over, sorry, I don't know what I did. That way, maybe. Okay. It's too sensitive, this one. Okay. So if we had that example where the matching had one match to 3, so I equals 1 match to j equals 3, I equals 2 match to j equals 2, I equals 3 match to j equals 1, this would have been a summation over u1 plus v, I'll just remove the summation and write out this explicitly, u1 plus v3 plus u2 plus v2 plus U3 plus V1. I could have rearranged it as U1 plus U2 plus U3 plus V1 plus V2 plus V3, which is basically that term and that term. You see what I'm trying to say there? So if I had this relationship, the cost of M is greater than or equal to that, because this is nothing but that, is what I've just said in the last 5 minutes. Okay? If that were true, please see what this means. So the cost of any feasible matching is greater than or equal to the sum of the row variables plus sum of the column variables. In fact, if you actually look at your min-cut max flow theorem, the first observation, that max flow is a lower bound on min-cut will look remarkably similar in the mathematics to what I just wrote there, except that instead of a cut, I have a cost here. The cost is always greater than or equal to the sum of the row variables and a column variables, which I'm maximizing. Remember, the maximization is to maximize this. The function is to maximize this, right? So I have a formulation where whatever I'm maximizing is a lower bound to a cost of any feasible matching. Okay? I'm going to go to the board for a bit. Same intuition. Let's go to the board. Okay, so we got, so this is the cost of M prime, let's say, and then this is sum of Ui plus sum of Vj values, two different worlds. That statement on the slide where I was speaking about, the one here, I'm now on the slide, wiggling my mouse. That statement suggests that the cost of M prime feasible matching is greater than or equal to the sum of Ui and Vj. It always is true, any feasible matching. Now, if I ever get to a point where I detect a feasible matching which is equal to that sum, haven't I automatically maximized this and minimized this? If that statement holds, the statement that cost of M prime is greater than or equal to that sum of those variables, the moment they become strictly equal, that means that I've maximized Ui plus Vj's and minimized the cost. Okay? So this is, the argument is, the proof is exactly similar, or at least reminiscent of min-cut max flow, where maximizing the flow, if the flow equals cut, I've maximized the flow, I have minimized the cut here. If the summation of those variables equals a cost of any matching, then you end up proving that the matching M, the perfect matching that you've got, is the optimal in cost, which maximizes Ui plus Vj's summation and minimizes the cost. Okay, that's what this is saying. If you ever get a matching, a perfect matching, which is equal to, you would end up basically having proving that the matching is minimum and the summation is maximum simultaneously, which is the goal, is to maximize Ui plus Vj summation, isn't it? The row variables and column variable. So this is how you kind of show that this formulation if you ever find any feasible matching, what do you do in Hungarian algorithm? You do an assignment when Cij is equal to ui plus vj. Okay? You always are going to pick those values such that it is in the reduced cost sense, in the reduced cost C prime matrix, the assignment is when you see a 0. We've already said that. So what would be the cost of an assignment in the reduced sense? Every time you pick zeros, the cost of the matrix is, you pick it as a 0. So the reduced cost is always picking values. So if the value in the reduced cost matrix is 0 plus 0 plus 0 plus 0, every time you see a 0, you're just adding a 0 there. So in the reduced sense, your cost, you're doing an assignment which has a 0 cost in the reduced sense. But then there's something associated with the reduced cost, the UIs and VJs. The UIs and VJs have to change so that it allows you to come up with an assignment in the reduced cost matrix. Okay? We'll see this algorithm. While we do this, it will become more and more clear. I've given you the grounding of what is happening. The main point is, when does the program stop? The program stops when you find in the reduced cost matrix not a specific, perfect matching. The moment the cardinality of your matching, where you're picking zeros, is n, you stop. And because you are doing this assignment in the special way, you can prove that if you look at the u's, those use values will be equal to the cost of that matrix, and because the cost is equal to the sum of u's, you can show that it is a min cost and a max sum of ui's and vj's, and hence you terminate correctly. That's the main argument of this algorithm. Subtle, but so each iteration, the cost is reduced. So reduced is nothing but C prime. So how does C change to C prime? By changing U's. U's and V's and U and V's are changing. So that's what's going to happen. You're making sure that while you're doing it, you're doing some assignments. We'll see what that means in an example. And because you are augmenting the objective function, because you're changing U and V's, your Z as a summation of U and V's is monotonically increasing in the number of assignments. Number of assignments is the cardinality. Initially, you could only assign possibly 1 or 2 if the n is out of n, and then next you would be either 2 or more. Every time the number of the cardinality is going to be the same or more, but the objective function is strictly increasing. Z becomes like you would have in simplex algorithm, like you would have it in max flow algorithm in Ford-Fulkerson. You're augmenting the objective function. The objective function is just keeping track of the sum of UIs and VJs, and that keeps increasing to a point where the moment you reach a perfect matching, where the number of the cardinality of the assignment is n, you stop. Okay? With all that background, we will look at an example and then see if we can go back to the theory and say, now I kind of understand what this theory was a bit more clearly. Okay, let's take this example, agent's task, n equals 5, so it's a 5 cross 5 matrix. Before anything, set all UIs and VJs to 0, okay? Now, there are two worlds in which you have to think about what we are going to discuss. I'm on the board now. So there's a world in which the original cost matrix exists. There's a world in which the reduced, so that's called the C, that's called the C prime. This is reduced cost matrix. So any cell ij, that is Cij here, the same corresponding thing will be C prime ij. So I throw jth column. Do you understand what I mean by this? Now, associated with, what I will be drawing are the UIs and VJs. So usually you'll be seeing a matrix in this form with UIs listed and VJs listed for a given state of the cost matrix. That is same as having UIs and VJs on the original, because all I'm trying to do is ensure that Cij, any Cij equals C prime ij plus Ui plus Vj. So how did I get this? I will just go back to that slide. Can you see the last line where I define C prime ij? C prime ij is Cij minus Ui minus Vj. I've just moved things around. Okay? I've written on the slide it's Cij equals, C prime ij equals Cij minus Ui minus Vj. This implies Cij equals C prime ij plus Ui plus Vj. You understand what I mean there? So I've just rearranged this. So every time you see a value in the reduced cost matrix, there'll be a Ui and there'll be a Vj out here. So Ui variable and a Vj variable. If you add to C prime ij, you would be getting Cij, the original one. Anytime, everywhere in this algorithm, that needs to be true. Okay? And that's what we are going to change. Initially, all of these are 0. So you're going to see it in the reduced form. Remember that this value plus the row variable plus the column variable has to be the original cost that you have out here. So what you have as the original cost is that matrix here. That's the original cost matrix. Initially, UIs and VJs are all zeros. Now, let's start with what this algorithm does. Okay? So algorithm has 4 steps. Step 1, step 2, step 3, step 4. The first 2 steps are one time for a given problem. The problem is given. For any given problem, the first 2 steps is to find a feasible values of UIs, feasible values of UIs and VJs. Okay? We'll see what that means in a bit. Some starting values that are better than 0. That's what step 1 and step 2 does. Step 3 does an assignment, attempts to match. Step 4 says, well, if my matching is not perfect, augment. If not perfect. Okay, what does the perfect mean? That is the number of the cardinality of the assignment is less than n, augment. And then you loop back in step 3 and 4 is looping continuously until I get my number of assignment n equals, so perfect, n assignments equals the capital N, which is the variable, how many rows and columns that I have. So if I end up assigning all the vertices, I stop. The stopping criteria is when the number of assignments is n. Okay? Now, let's start with step 1 and step 2. How do I find feasible values of UIs and VJs? So initially, before we started anything, they are all zeros. Okay? When they are zeros, the first step is saying that reduce. So by the way, your focus should always should always be on the reduced costs. Okay? So this is one universe. UIs and VJs are in a parallel universe. So they are sort of working in tandem. So long as the reduced cost matrix, everything inside those values plus UI plus VJ is Cij, that is basically being maintained. This constraint is basically being maintained. So if you look, so we are always going to maintain Ci, so let's actually call this Cij equals C prime ij plus Ui plus Vj. That's what we're going to maintain no matter what. First step is saying, so we are right now here, in the cost matrix, so this is the original cost matrix, isn't it? So that's where when we have not started the algorithm, that's what the cost matrix is. Subtract each row with its minimum value. So what's the minimum value in the first row? It's 7. What's the minimum value in the second row is 7, third row is 13, fourth row is 10, fifth row is 8. Is that clear? So if I subtract it, in the parallel universe, I'm adding that value to Ui. Okay? Why? Because I have to make sure that Cij equals C prime ij plus Ui plus Vj. So if I've subtracted something from the term, I have to make sure that, so if I have subtracted 4 from here to get, subtracted 7 from here to get 4, subtracted 7 from here to get 0, subtracted 7 from here to get 3, and so on. Let's take another example. Let's take third row. We're doing this for everything. The minimum is 13. So if I subtract 13, I get 0. Subtract 13, I get 0. Subtract 13, I get 2. Subtract 13, I get 0. 13, I get 1. Okay? If I'm doing for every row, I'm reducing that row by its minimum. And when I do that, whatever I've reduced has to be added back here. Why should I add it back here? Because, what did I say? For any value, if you took its row, that value, C, that is C prime ij is now 14. If you add Ui, which is 7, and Vj, which is 0, so Ui and Vj, 7 and 0, 7 plus 14 plus 7 plus 0 has to be the original cost matrix, 21. Okay? That's what you had done there, nothing, no big deal there. You're doing the same thing in the column sense. Now remember, these are my feasible values of UIs from the previous step. Now I'm taking the minimum in the columns. Okay, the minimum in the columns. In the first column is 0, the first column is this. Remember, this is what the matrix is. This is the parallel universe. Everything here is in the parallel universe, UIs and VJ universe, right? So first column is 0, second column is 0, third column is 0, fourth column is 0, minimum of the fifth column is 1. So if I subtract the column minimum from each of the columns, so first column doesn't change because the minimum is 0, second column doesn't change because the minimum was 0, and so on, all the way to the last column. Last column, the minimum is 1, so they change, they reduce by 1, and if you see, my Vi is now 1. Now again, at any point, if you take any value like that, C prime ij equals 3, Ui equals 10, Vj equals 1. If you add 3 plus 10 plus 1, it has to be 13 plus 1 is 14. If you go back to the original matrix, it would have to be the cost. Cij equals C prime ij plus Ui plus Vj. Is that clear, everyone? Okay. So now, this is an important insight which you would get if you saw this as a graph. Now, I want you to focus on this matrix and these values. These values here appear as labels to the vertices, right? So if you think of this problem as a graph problem, so all the rows are associated with yellow, all the columns are associated with the greens. Now, what you see is a complete bipartite graph. Every vertex is connected to every other vertex. Some of the edges are highlighted, some are not, but if you look at this, I'll actually go to the origin. So if you look at this formulation here, first vertex is linked to the, so first row is linked to the first vertex in the column. So the cost of agent 1, task 1 is 11, so the edge is 11. The edge here is 7, edge weight is 10, edge weight is 17, edge weight is 10. Can you see that? It's a bipartite graph view of the same thing. There's nothing more to it. Now, only thing that I want you to stare at is the fact that 7, 7, 13, 10, 8, 7, 7, 13, 10, 8 are the labels associated with the vertices, and 0, 0, 0, 0, 1 are the things associated with the vertices in green. So one is the vertices associated with yellow, the other was vertices associated with green. So there's a one-to-one mapping of this matrix to how you're looking at it. Now, can somebody tell me why are some of the edges out here in that illustration, why are they highlighted and what are they? It's obvious if you stare, but I'll let you think about why are they highlighted. What's so special about those gray highlighted edges? Some of them, those thick edges, some of them are single line edges, some of them are thick. I want you to look at whenever you see a thick edge, the gray edge in the illustration, what is the reduced cost in that matrix here? So yellows are the rows, the greens are the columns. So take any thick edge. Let's take an edge like this, or maybe we'll take this edge. Okay, that edge. So that's third row and fourth column. Right? Third row, 1, 2, 3, 1, 2, 3, 4. So what is third row and fourth column? Third row, fourth column, it's 0. Yeah? The reduced cost is 0. What about second, so fourth row and second column? Fourth row and second column, reduced cost is 0. First row and second column, reduced cost is 0. So wherever you saw zeros in that reduced cost matrix, I saw a thick line in the illustration. Obviously that's pattern matching, but what does it mean? It means that if you look at any edge here, so if you take, we'll take the first one that you did. What was UI plus VJ for that? Is that equal to the cost associated with it? Cij equals UI plus Vj. Let's take another example. Let's take that edge, third row, fourth column. What's the cost, original cost of that thing? Cij is 14. What is UI? 13. What is Vj? 1. Cij equals ui plus vj, isn't it? So wherever I had Cij equals ui plus vj, what is C prime ij? It has to be 0, because that is the constraint they're maintaining, isn't it? Cij equals C prime ij plus ui plus vj. When it's strict equality, then C prime ij has to be 0. And what did we say Hungarian algorithm is going to do? It's going to do assignments in the 0 places in the reduced cost matrix, because that is the most important part of it. So you understood what these zeros are, right? By the way, in graph theoretic sense, this graph, if you took the graph of green vertices and yellow vertices, removed all other edges except edges that have Cij equals ui plus vj, or C prime ij equals 0. So if you look at a graph, or another way of looking at it, if you took this matrix and drew a n times n bipartite graph with edges wherever you saw 0, that thing is called an equality graph. Remember that much like how you were augmenting the flow network, when you're augmenting the flow, isn't it? When you're augmenting the min-cut max, I'm going back to this analogy because there is a one-to-one correspondence of how we are processing the algorithm there and versus how we are processing the algorithm here. In the flow network, you had this special object called residual graph. All the augmentation was happening on the residual graph, which was not the same as the original graph that you're trying to solve. Here, all the augmenting will happen on the equality graph while you're solving the min cost problem on the original bipartite graph. So, which is same as saying that you're picking assignments on zeros rather than assignments on other cells that are non-zeros, okay? With that prelude, the entire action of Hungarian algorithm is in step 3 and step 4 looping. So we'll start with step 3. Okay, so we are here. That's your reduced cost matrix from the previous slide. In a parallel universe, you had your feasible assignments of UIs and VJs. All we did was do a row minimum, reduce the matrix, do the column minimum, reduce the matrix. And that's what UIs and VJs are. That's where we are at right now. Step 1 of, step 3.1, or step 1 of, substep 1 of step 3.1 is in the current state. Oh, before we go to the step, what is UI plus VJ summation? If you sum up these, let's sum up these. 7 plus 7 is 14. 14 plus 13 is 27. Plus 10 is 37. Plus 8 is 45. And then if you sum up these, plus 1 is 46. So the summation is 46. What's the size of your matching? You have not yet matched anything. The size of the matching is 0. So when you started this algorithm with some feasible values, your z values had your z, the objective function z, is worth 46, and the number of matching is now the number of edges in the matching is 0. So what is the step doing? What is 3.1 asking you to do? It's saying that in any row, if there is an unambiguous 0, go and assign it. Unambiguous implies that there are no other zeros in that thing. So, okay, and by the way, there's no order to it, although when you write a program, you have to follow a certain, do row 1, row 2, row 3. Essentially, the recipe for you is in any order. If there is a possibility for you to do an unambiguous assignment in a row, go ahead and do it. So let's do an unambiguous assignment. How many zeros do you see in the first row? There's only 1 0, isn't it? Okay, let's go and assign that. Now, once the agent 1 has been assigned to task 2, can task 2 be assigned to any other agent? So we simply rule those things out. Now, what about row 2? Can I do an unambiguous assignment in row 2? Can I do an unambiguous assignment in row 2? Answer is yes, isn't it? That's my unambiguous assignment. Are there any other zeros in that column that I've just assigned? There are no other zeros, so I don't have to scratch them out. I mean, here I've scratched them out here. There's no such zeros in this column, so I don't have to scratch anything out. What about row 3? Is there an unambiguous assignment that I can make in row 3? Ignore the scratched one out. There are the 3 other zeros in that row, isn't it? So I can't really deal with row 3. What about row 4? There's no other zeros. I have to ignore the ones that I've scratched out because I already assigned it somewhere else, right? So I can't, scratching out implies that that's been taken. Row 5, there's nothing else. Now, it turns out that by doing this, my matching has increased to 2. Now, I repeat this process from this state on the columns. Let's do the same thinking. I've done everything. I'm unambiguous in terms of rows. I'll do symmetrically on columns. Now, so this was a state in the previous slide. Can I do an unambiguous matching in the first column? Yes, I can pick this, which means that those 2 are gone now, because if I pick it on the column, I can't assign that agent to any other task. I've already assigned it to one task. I can't do it, so I just take it out. What about second column? Second column is already assigned. Third column is already assigned. Fourth is no other zero. Fifth is no other zero. So when I do the steps 3.1 and 3.2, I have 3 assignments. Okay. Now, in principle, do you see that all the zeros have either been assigned or scratched out? That won't be always the case, by the way. There's a small caveat that's coming up, but I'll tell you what the caveat is, and I'll come back to the caveat. I'll just give you a warning that there's some exception, and I'll tell you what to do with the exception, but come back to it at the very end in the next lecture, looking at the time. But the idea is that sometimes if all the zeros are not covered or assigned or scratched out, that means that there are multiple possible ways in which you could assign them. And then the goal after step 1 and step 3.1 and step 3.2 is to make sure that all zeros are either assigned or scratched. So if there is an impasse, if you are still seeing some zeros that have not been assigned or scratched, you can choose any one of them, and then proceed to scratch out the others. So the idea is to come up with one solution of the many feasible solutions. Okay, so that's the only caveat. I'll just skip this slide and come back to it. But in this case, this was a state in which we were in. From the previous thing, we assigned 3 and scratched out the rest, and none of the other numbers that have been that are not assigned or scratched out are non-zeros, isn't it? They're not 0 numbers. In the reduced cost matrix, the cardinality is 3, the summation is 46. We have not changed UIs and VJs, so that won't change. Now, I'll just bring up all the step, otherwise I'll lose my scribbling every time I flip. So I'll just get all of them and work. There's nothing, don't have to see this, just focus on this while I explain. Whatever I'm explaining will result in what you see on the other side, okay? So this was a state that you were in. That's your reduced cost matrix. The recipe for you is, maybe before we just go to the recipe, I want to tell you what you want to achieve right now. Right now, what you want to achieve is, let's go to the illustration, come down to, that's page 2, isn't it? Yeah, that's correct. Now, I want you to focus on the matrix and the graph. Do you see that they are saying the same thing? First, do you see those special red bits that I have highlighted? Those red bits that I've highlighted, they are a part of those heavy edges, isn't it? Equality edges. Assignment was always done on equalities. Yeah, can you see that? They were not done on the thin edges, they were done on the heavy edges, the gray edges. Now, my state, if you look at UIs and VJs, the UIs are all the same here, and VJs are all the same here. Now, what's the goal of 3.3? The goal of 3.3 is saying that there are some cells, if you see the cells in the cost matrix, some cells that are not zeros, right? There's some cells that are not zeros. I want to be able to have a view of them, okay? I want to be able to identify them in some special way. How do I identify them? Well, look at the graph view here. So, in graph theory, so this is a graph of where the equality edges are in bold, right? So those bold edges. How many, so let's assume that there is a problem where you have to identify what are the minimum number of vertices that you could mark or that you could select. What are the minimum number of vertices that you could select so that you cover all the equality edges. You are able to see all the equality edges from those vertices. What does it mean? So if I stand here, here, if I selected these three, between those three, have I covered all the equality edges? Just take a look. Yeah? All the equality edges are covered, isn't it? So there's a graph theoretic problem called vertex cover. Okay? Finding the minimal vertex cover is the smallest number of vertices that you could select that can see all the edges in the graph. Here the graph is an equality graph. If you just forget about other edges that are not equality, the thin edges are ignored. If you just look at that graph, the goal is to find a minimal set of vertices that cover all the equality graph. Why am I interested in that? It's because I will look at those that are outside them and try and change them to an equality. Augment UIs and VJs so that I have more zeros to choose from in the next iteration, or other zeros to choose from. Because I'm right now, in my way of assignment, I'm stuck. There are no other zeros to assign, and I can't do anything more right now. Okay? Only my cardinality is 3. I need a cardinality of 5. Okay? So the step 3.3 is towards that goal. So what it's trying to do is I've done the assignment. The goal is to, I'm just conscious of the time, but anyway, I'll try and pick up from where we left in this lecture in the start of the last one. Don't worry. So the recipe is you have a certain number of assignments already done. Mark all the rows where you don't have the assignments. Okay? This is an algorithm to find minimal vertex cover for a bipartite graph, basically, of a bipartite equality graph. so to speak. So mark all the vertices that are not assigned, and in each of them, if you see a 0, mark that column. There's only one 0 associated with this row. I'll change the row color to green maybe. So for that row, if wherever you see a 0 in that row, pick that column. And then if you see an assignment in that column, pick its corresponding row. Okay? So it's a simple recipe with saying that first start with an unassigned row. If you saw a 0 in one of the rows, in that row, any 0 in that row, pick that column, and if that column has an assignment, pick its corresponding row. And there's no other zeros in that row, go to the next one, next unassigned row. Is there a 0 in that row? Yes, it's this 0. Is that column, if it's not, so now pick that column, but the column is already marked because you marked it previously, so there's no point marking again, so it's already marked. And if it were not marked, you would have picked that. You would have picked if there is an assignment in that